So I've got some background content on what a soil test represents, and it goes into a little more detail about some of the interpretation side. Are we more interested on kind of background of soil testing, or do you want to just jump into what those numbers mean and how we got them? What's the consensus? So do we need to do background on soil sampling, what the translation of a soil sample to the analytical process, or do we want to kind of jump to the recommendation side? Recommendation side. Okay, great. So we're gonna hop ahead a little bit. I'll start with just this slide that I think is probably the most important when we think about soil testing as a tool, is that if you don't believe this, there's really no point in soil testing at all. We have to believe that there's a point, and provided this needs to be supported by data, that there's a soil nutrient concentration at which we're not going to see a response to fertilizer. If we don't have this, then we're just going to keep applying fertilizer because we're always going to see a response, right? But that's not the case. We see years where we have very impressive yields with low nitrogen rates. We see that with no phosphorus or potassium in some cases. As you look on the screen, as we move from the left to the right, essentially you're seeing that as you move from a very responsive soil to potassium, you kind of see those stereotypical outer margin deficiency symptoms on the left, and as we move from this to the left to the right, you're seeing the scenario where we're getting to a point where we wouldn't respond to potassium fertilizer. So this is the case that has to exist for soil tests to have some value in nutrient management. And some of the concepts, and I'll skip across some of the background after this slide. The concepts that are built on that, they ring true for the most part when we think about even our current cropping systems relative to some of the eras that Tim was talking about. I'll note in some of Bray's work, he even does call out and say, if we ever could grow 300 bushel corn, we should probably do things differently, which I think is a good indicator of the need to update and work on new techniques and new practices. But this is from probably the most widely used soil fertility textbook in undergraduate classes, and we use this book, and it's relating essentially the soil test level on the left to the probability of response to yield increase with fertilization. Tim talked about focusing on response to fertilization. That's the big question we're answering when we look at a soil test report. We want to know if we should fertilize or not necessarily what the ending yield is going to be, but are we going to make money or at least increase bushels from adding fertilizer to that given crop? And so this, I think, is kind of a nice relationship between these points. Something though, and I'll show quite a few data slides, but we'll hop through some. I'll take Tim's share of the time to share data and some graphs and figures. All the slides are available for everyone. Whoever wants a copy, I can send it to Darby and she can happy to share that around. But this is an indication where we're actually not even looking at response to P or K. We're looking at response to nitrogen, but in different environments of potassium levels. So this was some work I did up in Wisconsin before coming down to U of I, where we were looking at the relationship between soil test potassium levels and corn response to nitrogen. And I would say expectedly, as you move from the left to the right, in a low K scenario to an optimum or high K in this scenario, we saw a greater response to nitrogen rate. We saw increased yields, but also, I'll say, an expected black line there and curve an increase of diminishing returns as we add more nitrogen. And so in this case, certainly K was a limitation, and once we got to a sufficient level, then we were able to internally use that nitrogen appropriately for that given corn crop. There's no fertilizer applied in any of this work. It's all soil test levels without K fertilizer applied. So we're just looking at what is the nutritional value of the potassium in the soil itself without recently applied fertilizer within the last 12 months. Some trends and data. I been fortunate to be involved and help run the North American Soil Test Summary, and so that's where we aggregate soil testing data from private and public labs around the US every 5 years. I did the last one in 2020 and doing this one in 2025. And we summarize on a state level what's happening relative to K, pH, sulfur. We do use zinc as well, and organic matter across the lower 48 states and the Canadian prairie provinces, or excuse me, all the Canadian provinces now. And kind of singled out Illinois. This was a paper we wrote summarizing the work in 2020 I'll note that if anyone's familiar with PAQ Interactive, the late Quentin Rund was really instrumental in getting this running and worked with Tim on a lot of projects, but he was really fun to work with when I was doing this work in 2020. But if you look at the values that are kind of boxed for Illinois, this is a trend that I think probably mirrors some of the conversations that Dr. Margonot's brought up from the University of Illinois as well. The fact that for a long time we've been in a negative P balance across the state of Illinois, meaning that we're removing more than we're applying. And we actually see that trend kind of popping up in our median soil test levels, right? So this is across in Illinois, about 1.2 million soil samples that's summarized from the state of Illinois. And so certainly when you think about one number representing a whole state, it's probably meaningless to any given field, but you do see a decreasing trend across all those numbers. K is a little more fluctuating, but we've kind of got a gradient of native potassium moving west to east within the state, even north to south, depending on parent material. So last basic slide, and then we'll hop to some of the recommendation development content. This relationship here is kind of a textbook diagram that I put together for a paper a while ago, but it's the relationship that we at least expect when we start to interpret soil tests. Kind of related to what Tim had said, it doesn't always shake out as what we would expect to happen, but this is a relationship that's been pretty consistent when we think about soil nutrient concentrations, specifically of immobile nutrients. So a lot of the content I have today is phosphorus and potassium related. That's because undoubtedly those are the two nutrients that we've been most successful at of testing in the soil and predicting a response. I'll talk a little bit about micronutrients and nitrogen as well. That's just been a little more muddy when we look at the relationships between what we measure in the soil, at least with the tests we currently use, and the response to fertilizer that we get. But as you look at the black line on the screen of relative crop yield, which really relative crop yield just means the response to fertilization. So if you have a low relative yield, you had a high response to fertilization. If you already are maxing out at 100% relative yield, that means you didn't increase with fertilizer added. So it's just really a response metric. And done quite a bit of work in phosphorus loss with surface runoff and tile drainage. You can see this is kind of a expected relationship as we increase soil test levels, specifically phosphorus. We do at times, usually when we get to about 70 to 90, 100 parts per million, we start to exponentially increase the susceptibility of loss to surface runoff and tile drainage of phosphorus as well. That's a little different when you deal with manured systems versus just mineral fertilizers for the last 50 years, for example. But these relationships pretty much hold true in a lot of cases. And then the dots, or the green points, they show the probability of response to fertilization. And that's a really important metric that is in the background of a lot of recommendations in most Midwestern states, but it's not really talked about. I know we don't have the numbers, or I don't have the numbers for our recommendations, U of I, that says if I'm at a 10 part per million soil, what's my % chance that I'll get a fertilizer response? Iowa publishes theirs. I published them in Wisconsin when I helped update their recommendations, and I think it's a metric that we need because as farmers dealing with kind of risk aversion decisions, you need to know what are the probabilities that you're going to get a fertilizer response, given your soil, cropping system, and things like that. So, basic slides. We're going to hop over to some of the interpretation part, though. We'll go this way. So the elements of soil testing, Tim kind of covered. What I'll hit on more in more detail is this field calibration with yield response, and that's really kind of where the rubber hits the road for needing to evaluate a number that's developed in the lab. And so as you kind of think about the elements of soil testing, this is the part where there's really a lot of interpretation, I'll say directions that one can go, not as just the scientist, but as the soil testing lab, also the agronomist and farmer making fertilizer decisions though. And so this whole process certainly has error associated with every step, but what we're trying to do is hone that and try to minimize that error in general. I'll throw up a few quotes here and there. I do really like this, the title of this paper. Now, it has no relevance to my research whatsoever. You can't step into the same river twice, but you can stub your toe on the same rock. I would say that's about the same for soil testing and specifically soil sampling. You probably can't soil sample the same soil twice. Even in our 40-foot by 100-foot research plots that we have, we're not pulling the same core from the same exact place every time. And so when we start to think about the error or variability with soil sampling, soil testing, expecting a response, there is a specific amount of error that's associated. One of the demos I like to do at field days is in a 4-row plot, pull soil tests from each row and just show the variance across a very uniformly managed piece of ground. And it does vary because of all those steps that I talked about where error is introduced. What we're trying to do is shrink that error so that we can have a more predictable and replicable response and result. And those I kind of talked about in that slide. So I think one of the kind of interesting stories is the error that's associated with some of this process. You know, a lot of times we focus on laboratory interpretations or some of the stats that we're doing in decisions. But soil sampling is probably the place where we introduce the most error in many cases. This is an example from this spring. Blake and Marina are in the back there. They were taking soil samples in a grid sampling project this spring. We had two very different, I'll say, high and low tech options when we were sampling and what we were comparing. We were comparing some automated probes with samples that were taken with a back saver and enough oomph to get down into the soil. And interestingly enough, when we were starting to look at the amount of soil that was extracted, the depth we were trying to get to, so these were all 1-foot samples that we were trying to take. In many cases, because of different soil texture and moisture conditions, the automated probes were about 1.5 inches more shallow than what we wanted to be at. And they had less soil, especially in our silty clay loam soils. And this is a case where we really wanted we wanted this tech to work really well because it could really automate on-farm research and even research in our small plot trials. But the kind of ending story was that Blake and Marina out there running 4-wheelers around or gators around sampling grid points was just as effective and got us better data. And so that's something that when we think about kind of moving to different levels of technology, this has to be considered as well. Now, maybe you develop a different way of soil sampling, you get your way around that, but it's certainly something that's present within all of these discussions. Laboratory testing quality is something that I think is important to think about when we talk about the error associated with a value that you maybe get back from the lab or interpretation. But I think one of the most things that, again, comes out of this is that this is not the main point of variability in a soil test result. It's something that exists likely due to operational differences when we think about how businesses are run and laboratories are run, certainly different equipment in different labs as well. But this is largely, I would say, managed or accounted for through proficiency testing programs. Dr. Lacey's here in the crowd. He's really involved with ALTA, the Agricultural Laboratory Testing Association in Illinois. As Tim noted, that Illinois has got a pretty strong history of soil testing labs working together in organizations. And this process of proficiency is something that we use pretty often when looking at lab, we'll say, accuracy and precision across time. So I'm going to now flip across a few slides and move into some of the recommendation components. I told Darcy I would bring a lot of content and we can kind of move around, so to speak. So is anyone doing any soil health testing specifically for nutrient management decisions or has been involved in any programs? Got one hand in the group. All right, well, I'll talk to you, sir, about the next slide. So some of the things that we've come up, and again, these are kind of topics that I come across, at least questions I get from agronomists and farmers, so I want to hit on them and make sure that this information is out there. One of the things that we do in a interpretation or recommendation program is, and this is something I feel very strongly about, is we need to provide recommendations for all tests that are available in a state. I'll show a few slides a little bit later that really where our recommendations are at right now. There's specific tests that we have an interpretation for. We don't necessarily have the raw data within the state, but it certainly isn't every test that's available to farmers in commercial labs. And so one of the steps is that we relate the nutrients measured within these tests to other tests and see what the relationships are. Now, one might think, well, if we just do this enough times, then we only need to have data for one test and then we can just convert between them. But there's some big issues with that. One example is what you see here. I apologize for just using red versus white, but if you can kind of see the shaded in points versus the open circle points, those are really different soils with different mineralogies and soil textures having different relationships between tests. Where this is important is that the need for independently calibrating these tests really comes evident when we look at the relationships. Really, the only two tests that we have the best relationship for are the Bray-1 phosphorus test and the Mehlich-3 test that's determined colorimetrically, or with I'll say an older, not very widely used method. The most important relationship is probably what you see on the top left, and that's the relationship between what most soil tests in labs are measuring in Mehlich-3 phosphorus with an ICP determination. There was a question about atomizing that subsample of just microliters of the extraction, and that's the relationship actually up on the upper right that concerns me a little bit when developing recommendations. The way we get around that is we just independently calibrate every test, and I'll talk about how we do that. The soil health tests, though, I think are important to consider because they have become a little more prevalent when wanting to make a fertilizer recommendation, so to speak. The challenge is that a lot of the tests that try to estimate mineralization, specifically with phosphorus, again, I said we'll focus on P and K mostly, those have really shown a pretty poor relationship. And that's really because the mineralization of organic phosphorus is very different compared to nitrogen. Nitrogen is a much more biologically driven mineralization process. Phosphorus has a lot more inorganic chemistry that's important when we think about moving from an organic P or P associated with organic matter to P that's going to be plant available. It's not always just microbial activity. And that's why you see these kind of shotgun spread of points in the two left graphs compared to at least a linear relationship on the right. Then we're dealing with a specific extractant. And the challenge is, and this now gets into some of the calibration data sets, and I'll show a few of those, that when we relate soil test levels to grain relative yield or response to fertilizer, interestingly, when we look at the H3A test, which is part of a lot of soil health test packages, we can find a fairly similar relationship. These curves, or the way the data are responding to soil test level, is fairly similar. The challenge is, when you throw in this mineralization estimate, it really muddies the water. When we have a lot of these black points that are high in soil test levels but are below 100, that means that those crops or those treatments or sites are responding to fertilizer. So if we used the test on the right, it would say not to apply any phosphorus for any of these sites, where we certainly did see a response, an economic and agronomic response to phosphorus. We're looking for this coalescence of data where we can see a shape that's predictable. And it just didn't happen when we tried to estimate mineralizable P. That was using the CO2 burst test. All right, I'm going to skip through some of the extraction numbers. One thing I think is important to consider when thinking about other nutrients like potassium is the connection between soil moisture. In the last, I would say 6 years, how many people have had a discussion or heard something in the ag news about dry soil tests and we need to be careful with potassium and pH? I see a few heads nodding. That's certainly something that comes up a lot. Interestingly, we've been having more and more dry falls in the last, I'll say, 8 years. And so if you're dealing with soil test levels from 2 years ago, 4 years ago, likely it was a dry fall. Now, if we're using recommendations that are based on fall sampling, we don't have a lot of options. But that's some of the work working with Tim's group that we're excited to eventually provide spring and fall sampled recommendations. So you don't have to kind of guess, well, it was probably 30 parts per million higher in the spring because there was more moisture. What you're seeing here on the screen is, I'll say, an exaggerated relationship between soil moisture and potassium level. So essentially what we did, this was some work I did in Wisconsin, we pulled soil samples and analyzed them in field moist conditions. So we didn't dry them, we didn't grind them, we just mixed them up, we extracted the potassium, and then we measured it, as is, so to speak. And then we had samples that we put in dryers that would be a common practice for soil testing labs, where you're going to put them in there so you then eventually get to a point where you've got a consistent moisture. Maybe it's 24 hours, sometimes it's 36 hours, depending on the specific soil. But what we found, interestingly, now we were going from 1 day or 0 days all the way up to 336 hours, or over 10 days. You were essentially getting those soil clays to flay apart and pull more potassium out of there. Now, this isn't necessarily in a high clay soil. I'll say it's a relatively moderately aged loess over glacial till soil. The Plano series, which certainly comes into northern and central Illinois as well. But interestingly enough, we see this kind of very unique relationship between soil moisture and potassium that is really important when developing the recommendations. And so if you're in a point where soil sampling, it was too dry, you did pull the samples and you're dealing with a value that's shifted, maybe what your agronomist or what you were expecting, that's something that we're working on providing interpretations so you can use a fall versus a spring value and not have to kind of take the guesswork out of, well, do we need to adjust higher or lower, just antecedently based on what was happening in the soil. And this is some information about field moist potassium tests that we'll talk about. We are looking at that test within Illinois. This is kind of one of the last, I guess I have one more on micronutrients backgrounds before we hop into the response data. Darby talked about this, mentioned buffer pH as a question that came up, maybe about something that needed to be covered. Right now, we don't have a buffer pH calibrated for Illinois. So where most of the states around us do for making lime recommendations, the Agronomy Handbook does not use a buffer pH. It uses water pH, cation exchange capacity, soil color, and it kind of bins soils into certain groups around the state and says this is the relationship that we expect between soil pH response to liming. The challenge of that is pH is not a very good indicator. Water pH is not a very good indicator of lime requirement. It's a good indicator of if we need lime, but not how much lime we need. And so that's where buffer pH comes into consideration, and that's really why liming is probably the most successful story of variable rate technology. Because a buffer pH test in the lab essentially takes your soil, it adds a solution that has a very high pH, and sees how the soil and the solution react with each other. So you're getting an exact result of what that soil is going to react to, we'll say, a liming material. This is not necessarily lime, it's an aqueous solution, but we're seeing how that soil responds to trying to increase the pH. And that's why variable rate liming has largely been the most successful compared with P or K or nitrogen, because you're getting a test value that sees how a soil responds. And that's usually been the story there. I know there's some retailers in the state who have switched to using a buffer pH method for their recommendations. And we're in a lot of discussions about and working with Dr. Margonaut's group, Dr. Bob Miller with the Soil Test Certification Program, ALP. We've got some projects that are looking at how quickly we can develop liming recommendations that have locally calibrated buffer pHs for the state of Illinois. And so I think that's not in the too far, I'll say it's in the near future, whatever that term actually means for delivering. But I think we can have some pretty consistent numbers within a year or two on getting lab data and field data for that. So Tim talked a little bit about nitrogen soil testing. I won't go into this too much because in general, if we think about, there's been two main, I'll say, efforts or thrusts within nitrogen testing. A pre-plant or pre-side dress nitrate test. Those kind of boomed and busted in the late 90s or early 2000s, I'll say. They were kind of developed specifically for areas that had more prevalent manured areas, even though they don't necessarily work the best in manured systems because there's a lot of nitrogen hanging around that isn't in nitrate form. And these tests were kind of effective at directionally saying there was a lot of nitrate in your system or there wasn't. The Illinois soil nitrogen test, I'll leave Tim to describe that more in detail than I'm familiar with at this point, but it was developed by Dr. Mulvaney at U of I, essentially looking at amino acid and sugars that are able to become plant available nutrients. And the challenge, I think, wasn't too different for any of these tests, or that generally they're more directional when we look at the management. And so, for example, this is a data set of mine on some end response trials. This is the corn yield with 0 nitrogen applied on the left and center. It certainly has a relationship with soil nitrate in the upper foot, but it's very hard to say what the fertilizer rate was needed at any of these sites. On the far right, you're looking at the relationship between that 1 foot soil nitrate and the economic optimum nitrogen rate. And there's it's a very messy set of data to try to piece apart and say, you need 150, you need 125, you need 180 pounds of N. So that's been the big challenge with soil nitrate testing in general to this point. And I think I really like showing this graph because I think it's important enough that the range of, we'll say, corn yield in this case, supported by soil nitrogen varies quite a bit. This is from our Central Illinois recommendation data set that updates the N rate guidelines. And this is showing the fraction of yield at the optimum N rate. So we're maximizing yield, and that's where this value is coming from. This is the fraction of the yield that we've maximized that's supported by the soil. We just use the control plot to estimate that, but it ranges from 2 to 80%. So tying this down certainly is a big challenge that we'd like to do in soil testing. We just don't have the tests, I would say, to do it at this point. All right, micronutrients in soil testing. Who's looking at micronutrient soil test reports or tissue test reports? A few hands. Marcos, I know you're doing that in your research. So I'll throw a few slides out here, and this is kind of just to spur a little more discussion. There's some ongoing research around the state, and we've got a few projects that are looking at this as well. The biggest consensus is that soil testing for micronutrients has generally kind of failed us in terms of predictability. I would say soil testing for zinc has been the most consistent in having a relationship with response to yield. But boron, manganese, even if you're thinking about looking at something like iron, we just haven't had that clear relationship between soil test levels and yield response. And this is some, I'll say, shotgun spread data from some work in Iowa. This was done in the research group that I did my grad work in. And this is comparing soil nutrient levels for micronutrients with plant nutrient levels. So this is not fertilizer response data, but this is just looking at the concentration in the soil versus concentration in the plant. And these are pretty weak relationships all around. And I would say these hold pretty consistent in many cases. The only place I've seen it improved, and you see zinc down here on the bottom, isn't very impressive here. We did see a little more clean and clear zinc data in Wisconsin when we did some of this work. Interestingly enough, when we compare plant and leaf data, so total plant nutrient concentrations versus our leaf samples that we'd usually use for diagnostic relationships, these still aren't very clean when we think about trying to predict one from the other. And so what this is telling me is that there's a little bit of a gap in terms of wanting to make fertilization responses, specifically with micronutrients if you're going to be using tissue testing or soil testing. So what do? Well, characterize your soil probably based off of soil organic matter, texture, and then if you've seen responses in the past. All right, we're gonna hop over a few more slides here. I want to hit on this specifically, though. This is something that I think is important enough to hit before when we're thinking about kind of the background components of recommendations and interpretations. Usually, all of our recommendations are communicated in pounds per acre. The labs are measuring values in parts per million when they're coming out of their analytical equipment. And we're kind of the only state in the north central region who deals in pounds per acre instead of parts per million. It's not necessarily an issue for a few reasons, but I think we're kind of introducing more error into the system because of it. So let's run through kind of some calculations and scenarios here. So if we're working off of so an acre furrow slice is how deep? It's up on the screen. Technically, an acre furrow slice is 6 2/3 inch deep, right? I still don't know where that actually came from. I've seen the number used for over 75 years, but I don't know where that actually came from, if there was a specific plow depth that was measured with that depth. So we use 7-inch depths within Illinois for soil sampling depth. So we're the closest state to 6 2/3 that you can get. Indiana uses 8, we use 7, Iowa uses 6, which is kind of a mess for soil testing labs having to deal with customers across all of those states, although they handle it pretty well. So if we deal with a scenario where we've got a 15 part per million P, so if that's what the lab measured, whether it's colorimetric or ICP, they measured 15 parts per million, a 7-inch soil sample depth, We're going to assume this is a pretty typical bulk density, the number of feet or meters in an acre, and 1 part per million equals 1 milligram per kilogram, just another conversion. And if you take the bulk density area and 1 part per million and 1 milligram per kilogram, that averages out to about 0.892, so it's a coefficient we'll use. So if we're dealing with a 7-inch sample, we have a 15 part per million soil that's measured from the lab, that technically calculates about 31.7 pounds of P per acre. Not 30, but 31.7. That's due to that 1/3 inch difference across the soil. That's what's leading to that different number. Now, the expectation is we just multiply by 2 in most cases, and that's the conversion. Now, in our case, it's not as big of a deal. In other states, it is. If you're dealing with a 6-inch sample, now you actually have 27 pounds of P per acre. 6 2/3 is that exact 2, and an 8-inch you actually have more, 36.1. The biggest challenge, and I kind of skipped one of these slides of what a soil test represents, is that dealing in pounds per acre doesn't make a lot of sense for soil nutrient concentrations because the plant does not see that pound per acre. That is only what we're pulling out of the soil when we run an extraction through. We bombard it with acids. We try to keep all that phosphorus out of solution, and then that's what we're measuring in the lab. It's not going to relate well to a pound per acre of, say, crop uptake. It's just an index of availability. And because in general, remember, this soil test has to represent from emergence all the way until physiological maturity, the plant uptake. Mechanistically, we don't really need a good relationship. We just need a statistical and predictable relationship between soil nutrient concentration and fertilizer response. So that's one of the challenges that I think we'll start to introduce some more fact sheets and conversions, because dealing in pounds per acre does provide some challenges in that we think of it as kind of a mass balance, right? My corn crop needs 120 pounds of P relative to our soil test P. That means I need 120 pounds in my soil test level. But that's not really the case, right? We don't necessarily need to be dealing with 60 part per million soils to maximize yield, even though that corn crop may have needed 120 pounds of P. Usually it's going to be a little bit lower. That's kind of an exaggeration, but it's an important example that soil testing is just an index of availability. We can't use it as a mass balance where we put on this amount, we have this amount in the soil in pounds per acre, and then we remove this amount. It just doesn't hold up. And usually it doesn't hold up because there's a term I really like called you have to pay the reaper. And the reaper is cation exchange capacity, leaching, use efficiencies. All of those things mean that we can't have this perfect kind of cycle of nutrients, that we always have this perfect equation that equals 1, for example. So that's a big challenge. We talked about this a little bit about what soil tests represent. Something I want to get into a little bit, and I think has led to some challenges, especially with potassium in soils similar to Illinois and Iowa and Minnesota as well. We didn't see this much in Wisconsin. But the relationship between nutrients that we measure in a soil test versus just the amount of nutrients that are hanging around in the soil in different forms is something that's a little more important than we've given, we'll say, credit in the past. And we're seeing some clarity because of that, and that's probably why I bring this up mostly. On your left, so this is from a long-term study where there are annual rates of 0, 80, and 160 pounds of K applied. On the left is a routine Mehlich-3 result from I think we had 11 years and 4 replications within these specific treatments. And unsurprisingly, as you increased annual K amounts, you'd increase your soil test level. Now, what you see on the center and the right are different fractions or different soil tests where we're trying to measure total potassium, or the amount of K that's potentially available, whether it's hanging out in soil minerals, hanging out in the edges, or between layers of minerals. So we wanted to know what's the total potassium level. And we still saw an increase with the amount of K applied every year. And this is an EPA standard method for determining total nutrient concentrations in things like biosolids, soils, plants to a certain extent, but there's a little bit different method there. But as you can see, we certainly are dealing with a higher value here when we look at the y-axis going up to 250 versus 1800. Now, what's happening on that right side is what we actually did was run an extraction method that I'll say sucks potassium out of the middles of clay to a stronger degree than this acid. Nitric acid is still nothing you just want to play around with in the lab, but essentially what we did with the test on the right was we were dealing with a very strong sink-source relationship between the chemistry, and we were pulling potassium out of those interlayers of clay. Remember from maybe a soil fertility class, you think of soil clays as sheets of paper on top of each other. Between those sheets, you can get considerable amounts of specifically potassium. And one of the interesting things when we look at the amounts here are, we'll say this is 1x at soil test potassium levels. Our EPA standard method was about 10x the amount that we extracted with our routine analysis. But we were about 20 times higher with the non-exchangeable potassium. And so we had almost double the amount of K that we were pulling out of the soil than just a quick melt of the soil minerals. What essentially we were able to do with this specific test was we were able to start dissolving minerals so that we could pull nutrients out. The reason I talk about this is the difference between these relationships. You can kind of see more of a flat relationship here. This is certainly a more exaggerated response variable. But because the exaggeration is a lot lower, we essentially have a higher reservoir of K there that we don't pick up in our routine tests. Where I think this plays a role is when Tim showed some of the regions of the state where we'll say our state's broken up into cation exchange capacity for recommendations. We can use tests like these across a survey of soils to say this soil does have a more amount of native, I'll say reservoir of potassium that could be leading to more plant available potassium than your routine test is measuring. Now we're not going to run this test, the center or the right, on every soil sample. But if we can create maps to have predictable inherent soil properties, that's where I think there's some value in improving regional recommendations. And because clay chemistry is a lot of fun, you can see in a three-dimensional diagram where those yellow potassiums, but also ammonium is hanging out there. That little pink sphere is ammonium in there. There is non-exchangeable ammonium that hangs out in those places that's available for our crops. And I had to throw some mineral pictures up here. This is where we're trying to pull potassium out of. These are not uniform soil constituents, but we're trying to extract a uniform amount or uniform concentration out of these areas within the soil. And certainly if we think about the soils that we have in Illinois, our difference when they're wetting and drying is pretty evident, especially in the cracks that we see. So now I said I wouldn't go through too much background, but we'll go through some of the calibration steps here. So there's three maybe main steps to get to guidelines that you see in a fertilizer recommendation from your soil test value on your report. The first one is and Tim showed some of the graphs and I did as well, we have to have a response between soil test level, a relationship between soil test level and fertilizer response. And that's the correlation component of this, where we're essentially being able to predict response with soil test levels. The second one is we need a rate calibration phase. So we need to say, if I have this soil test level, this is the optimum rate that's been identified through hundreds of trials that have been done. And then there's kind of the other component, because based off of our, I'll say, build and maintain philosophy, where we're trying to optimize soil test levels and keep them there, is that there's really an important component of removal when we think about what we're removing out of the field relative to how our soil tests will change as well. Essentially, we look at the relationships between soil test phosphorus and relative yield in a few different ways. We try to explain them with some different mathematical or statistical models. Interestingly, none of these, which are the four most common, are used in the agronomy handbook. Roger Bray ended up using a model that was based off of some German work that essentially was looking at a point where you never really reached a maximum. You just kept increasing. It's called an asymptotic relationship. So you just kept increasing a little bit more and more. I would say that's not very realistic, because we do find places where there's a threshold, you stop responding to nutrients. And so that's one of the big differences, I think, in some of the work we're doing now versus what's maybe in place. And this is the kind of an easy way of defining that response relationship. I talked about that earlier. These are our data from 2 site years of research and response data, looking at, this is Bray 1 P levels and Malick 3 soil test K levels with corn and soybean together relative grain yield. And we wanted to find these relationships between the two variables, and we identify essentially where we start to see a flattened off response to fertilizer. Now there's certainly some noise here, which is expected, but this is the point where we're not consistently finding response relative to on the left side of the graph. One of the important things that I talked about earlier is the probability of response. Now this is data showing across all replications and site years. This is about 120 site years of phosphorus response data that we put together up in Wisconsin. But it's a good example, and I'll show some examples of the Illinois data and how it compares to this pattern. But what we want to do here, and this is the process that I went through up there, is we essentially pulled apart this relationship and said, where do we flatten off within this black line? And then how can we break apart different levels of specifically interpretation classes. So we're looking at things like very low, low, optimum, high, and excessively high for phosphorus in this case. And I have it in pounds per acre here. And essentially what we were seeing then is we were breaking apart these interpretation classes by the probability of response. And where I think this comes into play is especially when we're dealing with scenarios like today when phosphorus fertilizer is at a price where we really need to know if we're going to get a response or have a high probability of response. And that's where this type of interpretation analysis can kind of piece apart some of the information. And we can do the same thing with potassium. Now potassium in my experience has a little bit cleaner relationship in terms of response. That's not always the case in most soils depending on what your mineralogy and parent material is. But essentially this relationship of increasing relative yield to a point where it flattens off, and we decrease the probability of response as we increase soil test levels. Now we can look at this a little bit different way, and again this is kind of the background of the numbers that we assumed came out and developed things in the agronomy handbook, but this is how we look at the numbers that we've developed recommendations in other states as well. Now if we just look at grain yield increase, so we're kind of looking at the opposite thing of relative yield. Instead of fertilizer response and as a percentage, we're looking at the grain yield increase in bushels per acre when we're dealing with different soil test levels. Now this is an example using Bray soil test potassium as well. It extracts about 85% of a Malic 3 test, so that's why these numbers might look a little bit different. But essentially we expect this kind of breakpoint relationship where we come to a point where there's no more yield increases. Now you see these fairly dramatic yield increases with potassium and phosphorus when we're really low enough. But those are mostly in soils where, for example, in potassium, where you're dealing with sub 50 part per million K. Those are kind of hard to find sometimes. But I think the more important part is where we start to break point on the right side. And then what we can do as well is break this out into interpretation classes and say, what is the at least average yield response to P or K within these scenarios in these different classes. So if we're very low, low, or optimum, what are the expected yield responses as we're moving across this data set? The final part that we really have to come to a recommendation through is the calibration of the rate combination relative to soil test levels. And essentially what we're seeing here is the relationship between responsiveness to P fertilizer, and I'll show the K fertilizer one in the next one, or next slide, and our soil test levels. So as you're moving from a black line to the hashed and up, or essentially as you're going up from the lower triangles to the upper triangles, we're going from a low testing scenario up to a high testing scenario, where our optimum P, and then we'll show K rates, are decreasing as we're increasing soil test levels. Interestingly enough though, we never are able to, we'll say, fertilize our way out of a low testing scenario. And this is something that I think is important enough to spend a little bit of time on, that where the challenge is when our bulk soil P or K levels are so low that we're not allowing for even our recent fertilizer to give us our maximum yield potential. And interestingly, this is kind of against, to Tim's point, against what I was trained as, is that you can always fertilize your way out of a low testing scenario. If you've got 6 part per million Bray P, you put enough phosphorus on there and you're going to get maximum yield. But we just didn't see this in this data set. And this is one of the larger calibration data sets that's been put together. Essentially, we saw that you needed to get up to at least a optimum category before you're starting to maximize yield also with some fertilizer. And for K, we kind of saw the same thing. It's a little more of a messy relationship, or not as necessarily as clean on the corn side, and the soybean side kind of coalesces to rates that are a little more similar. But it kind of says the same thing, that if you're low enough testing, you can't, in one given year, you can't fertilize your way out of it. Now, you can increase or maximize your ROI in a given year, and that makes a lot of sense. But in terms of reaching a yield plateau that you're wanting to compare with other soil test levels, that's probably the biggest challenge, is that we're not able to get to those yields where we would want to with our optimum testing categories. Now, there's a few methods, I'll say, that are used in soil test interpretations, and really two prominent ones. And one of them is a short-term versus a long-term mentality. The short-term mentality is called sufficiency philosophy. Essentially, you're fertilizing for that crop every year and only that year. Now, for that, you need a lot of this calibration data to show what that optimum yield is. And if we were comparing this to the sufficiency philosophy, we would not at least reach, we'll say, maximum yield levels for that given scenario. Where this usually comes into play are in more arid environments. As you move into Kansas, Nebraska, South Dakota, they're usually dealing with lower yield levels and more annual risk than we might have with our yield levels in the central Corn Belt. But what we use in Illinois is a fairly traditional build and maintain concept, at least the way the recommendations are offered right now. And that kind of strict interpretation is there's a nutrient amount that we need to build up to, we maintain that level, and then that's essentially maintained through replacing removal, assuming that the relationship between our soil test change and removal is what we expect it to be. I talked about nutrient balances and how they don't really work because of the unit of a soil test and what that really means. But again, this is kind of the prominent concept across the Corn Belt, and what we use in Illinois is related to this build and maintain philosophy. Now, a few things that are important within all of this. I saw one of the green plans out there in the front. On a lot of fertilizer recommendation programs, and especially the way the numbers are written in the Agronomy handbook, everything is based off of a 4-year build. So essentially what you're doing with your given soil test level is you take the level you want to be at, you take the level you're at, and you divide it by 4, assuming a amount of fertilizer you need to increase that soil test level every pound or every part per million. Now, the challenge with this is different states really took a lot of different philosophies. Iowa used a 4 to 6, Wisconsin used a 6 to 8, I can't remember what the tri-state recommendations are using, but essentially this is a component that I would like to make a little more editable or flexible or filterable when you're going through the recommendation process. Essentially, is this a rented versus owned farm where you can afford to build in a current timeline that makes sense economically? So that, I think, will be a change and an option that we'll be having in the future as well. Tim already showed these curves, talked about some of the data behind them. One of the most important things that I would say on the phosphorus side is we don't actually have calibrated data yet, I'll put the yet in there, for the Mehlich 3 ICP test in Illinois, even though I would say most of the samples are measured on an Mehlich 3 ICP value, and they're back converted to a Bray or Mehlich 3 value. For the majority of soils, this isn't necessarily always a huge problem, but it introduces more error. And so I think this is really important when talking with agronomists, retailers, soil testing labs. I would feel much more comfortable if we provided recommendations for the exact test value that you were getting back off of the machine in the lab. And so that's, I think, where we probably are going to be going forward, is providing recommendations for any test that's run in the lab. And it's kind of I'll say, low-hanging fruit research work for us to do, because then we provide data that essentially can reduce the amount of error within that process of interpretation. And we don't really need to go through on the case side. One thing I will note on these interpretations here, and this kind of gets into some of the philosophy. I talked about earlier about those kind of models where we would expect yield response to plateau, right? So these lines here that are showing the oats and wheat, the soybean number, the corn and alfalfa and clover curves here. Tim showed some of these as well. What I expect to probably change as we look at some newer data, and it's showing true as our students are working this up as well, is that these curves really start to flatten off most cases. They're not continuously increasing until you start to get to a soil test level within this, we'll say, the maintenance range, or where the subsequent yields are dependent on K fertilizer. And that's not necessarily going to drop or adjust the soil test critical levels or concentrations where we would expect a fertilizer response or not. It's just going to change the way we look at a lot of the data that underpins a lot of the recommendations and interpretations. We don't really have interpretation classes within Illinois. We've got these, of course, bins or thresholds of nutrients to consider, but certainly these aren't necessarily the same thing as the lows, mediums, and highs that you see maybe in other states. We do have that subsoil P supplying power consideration, which Dr. Margonaut's kind of addressing and finding maybe isn't as consistent or predictable as what we'd think. Predicting subsoil nutrient concentration in general is very difficult, and it's not as predictable as what I would say is usually seen. So we've got 2 minutes left. I'm going to throw into a few of details on the recent research that we've been doing in collaboration with Tim's group and Dr. Brad Jorn at Precision Planting as well. Tim showed a map of where research had been done in the 20s and 30s and 40s around Illinois, and you're kind of excited to start to build some of that capacity back up. The dots that you see on the map here are a combination of sites that we have in collaboration with Cropsmith and Precision Planting, some of the research center sites, and some on-farm sites looking at P&K research. That's all going to these goals of updating recommendations for the state. And I think one of the important things that we're excited about is that we're not just trying to do what every other state has done and kind of just get up to par. Right? We don't really just want to get up to par with everyone else and say, well, we did the exact same thing, so we're good. I think the exciting thing is to think about what new science or technologies can we apply to get to a more accurate and precise prediction of fertilizer response. And so within these studies, it's not at every site, but we've got corn and soybean every year, conventional strip till and no-till comparisons, a lot of rate and timing comparisons, and then certainly the amount of sites that we have across the state, I think will represent these soil regions well that kind of, I'll say, sprung the current way we think about soils in response to P&K around the state. And when we compare where the old soil fields were, I think we're going to be able to cover the state really well, specifically looking at gradients of soil inherent properties around the state relative to the subsoil P supplying map, and cation exchange maps. I'll flip past this because we've kind of seen some of that in data interpretation before, but this is an example of some of the recent work that Franco, a master's student, worked up that we presented at the North Central Fertility Conference a few weeks ago. So this is just some of the preliminary data looking at the relationship between Mehlich-3 soil test phosphorus, Mehlich-3 soil test potassium, and relative grain yield. This is just using one method, so we've got more work to go interpreting other methods, but this is kind of going to be the way that we can feed updates within the system as well. I'll skip this point, and one thing I do want to talk about is the other components that when we're doing this process that we're considering. So how do things like tillage practices, specific crops, and base saturation relate to this specific research? This is some older work that I had done a few years ago, looking at how do tillage practices change, how we go through this process. And essentially it's relating two different scenarios where we had long-term tilled systems or tilled fields and no-till fields, looking at can we take different soil sample depths and predict responsiveness. Probably one of the things that came out of this, which was I'll say good to hear in terms of simplicity of the system, is that in this case, now this was dealing in Iowa and Wisconsin, combining some data that the 6-inch sample depth actually provided the best predictive power of responsiveness to phosphorus, regardless of tillage systems, whether you're going with a shallow sample or a deep sample in general. I don't know if that's always going to hold true, but it's something that we're looking at across Illinois right now as well. The only other thing I'll talk about, because I've got some questions this week, is the relationship between base saturation and extracted K and the ability to predict a fertilizer response. So this is a comparison between two different ways of trying to estimate the available potassium to the plant. On the left, we kind of have our method that we've talked about quite a bit so far. We're relating soil test potassium levels to yield response or relative yield. And we've got some expected response curves where we can say, yep, we're seeing a point at where we're not responding to fertilizer, and below that we do. Where we ran the same sample set and looked at the percent of assumed potassium that's taking up exchange sites. That's how I would recommend kind of defining base saturation K. I'll say assumed because it's not a direct measurement. It's just kind of an estimate of the K that we measure in a soil test relative to the K we measure in other soil tests for nutrients. But this was a little bit more of a messy relationship, and actually we didn't get any of these models to fit this data here. And so one thing I'll caution, especially in the economic times right now, is basing potassium recommendations off of this method. Because if you're being told that you need to go to 3, 4, 5, 8% base saturation, that's probably not going to be economical in most of our soils in Illinois. You're going to have to be applying about 700 to 800 pounds of K2O per acre to reach that. It's just simply not a predictable way of saying this is how we can get to a value that we can expect fertilizer response. So with that, I think I'll stop there, and I've got some extra content that I think probably will fit into some of the questions on the panel discussion as well. Thanks for the attention and suffering through all of the data and slides. If you want any more information, feel free to ask me after, and I'll be happy to share it. Appreciate it.